In this presentation, we will consider one special problem related to prime numbers. So let's get started. Write a program to check whether a number is prime or not. This is our problem statement. We need to check whether a number is prime or not. But before solving this problem, we need to understand some basic terms. So let's understand some basic terms related to this problem. The first term that we need to understand is prime number. What is a prime number? A number greater than 1 is called a prime number if it has only two factors, namely 1 and the number itself. Like for example, we have 2, 3, 5, 7, 11. These are the numbers which are having only two factors, 1 and itself. On the other hand, composite number is a positive integer which is not a prime number. That is, which has factors other than 1 and itself. For example, 4, 6, 8, 9, 10. Not only they have factors 1 and itself, but they also have factors other than 1 and itself. Therefore, they are composite numbers. Now let's address one important question. Is 1 a prime number? No, it is not a prime number. Because according to the definition of prime numbers, a prime number is a number which has exactly two divisors, 1 and itself. This is very important point to note. But 1 has only one divisor, that is itself. Therefore, it is not a prime number, right? Another reason could be it violates the fundamental theorem of arithmetic. Now, according to this theorem, every positive integer greater than 1 can be written uniquely as the product of primes. This simply means if we have a positive integer greater than 1, then we can write that positive integer as product of primes, and that too uniquely. Like for example, we can represent 9 as 3 into 3. Now what does this term uniquely means? This simply means that no matter what, we can represent 9 by 3 into 3 only. The only prime product of this number is 3 into 3. But if we consider 1 as a prime number, then it should also represent this number uniquely. But here you can see this clearly that 1 would not be able to represent this number uniquely. As we can write 9 as 3 into 3 into 1, we can also write 9 as 3 into 3 into 1, and so on. Therefore, as 1 is violating the fundamental theorem of arithmetic, therefore we can say that 1 is not a prime number. If it is really a prime number, then it should represent the number uniquely. But it is not representing it. Therefore, it is not a prime number. Now, the big picture. In order to find whether a number is prime or not, we first need to calculate the square root of that number. This is very important. And then we divide the number by numbers less than or equal to the square root of that number. That means first we need to calculate the square root of the number, and then we need to divide the number by the numbers less than the square root of that number. If it is divisible by any of the numbers, then we can say that the number is not a prime number, else it is a prime number. Like for example, suppose we need to find whether 23 is a prime number or not. The step 1 would be take square root of 23. Square root of 23 is nearly 4.7958. We can take an upper limit of it, which can be 5. Now step number 2 is divide 23 by numbers greater than 2 and less than or equal to 5. If it is divisible by any of those numbers, then it is not a prime number, else it is a prime number. As simple as that. We will simply divide 23 by numbers less than or equal to 5. If it is divisible by any of those numbers, then we can say that it is not a prime number, else it will be a prime number. As 23 is not divisible by any of those numbers, therefore we can clearly say that 23 is a prime number. By using this idea, we can write our code like this way. This is our code which checks whether a number is prime number or not. Here I have divided this code into 3 parts. This is part 1, this is part 2, and this is part 3. Instead of understanding this code in one go, we will try to understand this code in 3 different parts. So let's get started. Part 1. Finding the square root. Now how do we able to find out the square root? This is the code which finds out the square root of the number. Here I have declared two variables x and val1, and that too of integer type. And to this val1 we are providing the value returned by this particular function. Now it is quite complicated looking function, but it is not that complicated to understand. First of all, we need to understand this particular function sqrt x, what this function does. Sqrt function calculates the square root of the number, and it is available in math.h library, therefore we need to include this library here. So as we know already in our logic, we need to calculate the square root of the number, therefore this function helps us in calculating the square root. Now what is the syntax of this particular function? It accepts the double value and returns the double value. Now you might ask me this question. Here you are providing an integer value to this function. And here in the syntax it is written you have to provide a double value. Is it not violating the syntax? Let me tell you one important point. Here it is not violating the syntax at all, because from integer to double there is no loss in precision. Therefore compiler will do implicit conversion. As we know this thing already, if we are converting from one type to another type and there is no loss in precision, then compiler will automatically do the type conversion. Here integer will get converted to double implicitly as there is no loss in precision. Therefore there is no problem. It is completely legal. Apart from the square root function, we need to understand the ceil function as well. What does it really mean? Ceil function returns a smallest integer greater than or equal to x. And this function is also available in math.h library. Syntax of this function is similar to that of square root function. It accepts a double value and returns a double value. Now let's consider one example in order to understand this code in a better way. Suppose x is equals to 2. Then the square root function will calculate the square root of 2, which is equals to 1.414. It is an approximate value. It might be greater than 1.414. Now we will provide this value to the ceil function, right? Now what will ceil do? It will return a smallest integer greater than or equal to 1.414. So the value greater than 1.414 is equals to 2. Therefore 2 will be stored inside val1. Again we need to understand that ceil function returns the double value. It might be 2.00000, but as we are storing this value inside an integer variable, therefore the decimal part will get truncated. Now after calculating the square root of x, we need to consider our part 2, which checks the divisibility. This for loop runs from 2 to the square root of x. As we know, we need to check whether x is divisible by any number less than or equal to square root of x. So we need to run this for loop from 2 to square root of x, and then we check whether this number, that is x, is divisible by any of the number less than or equal to square root of x or not. If it is divisible, then we set the count value to 1, which is initially set to 0. Now obviously, the next step is to check whether a number is prime number or not. And we already know if count is 1, then it is not a prime number, else if count is 0, then it is a prime number. But apart from checking whether count is equals to 0 or not, we need to check these base cases as well. As these base cases will not get covered inside this for loop, therefore we need to check them separately. If a number is a prime number, count must be 0. Apart from that, if user enters 1, then it should print 1 is not a prime number. That's why we have written here val2 should not be equal to 1. Or we should check if the number entered by the user is 2, then it should print that 2 is a prime number. Similarly, if user enters 3, then it should print 3 is a prime number. Okay. Now let's execute our code. Let's run this code now. It asks us to please enter a number. Let's say we entered 2. It says 2 is a prime number. Yes, 2 is a prime number. Let's execute this once again. Now let's enter 8. 8 is not a prime number. This is correct as well. Let's take one more case, 23. 23 is a prime number. We can clearly see that our code works fine, right? Okay friends, this is it for now. Thank you for watching this presentation.